Now let's understand fundamental theorem of arithmetic. Every composite number can be expressed as product of primes, and this factorization is unique apart from the order in which the prime factors occur. Now let's understand some basic terms like composite numbers here. Composite numbers, prime numbers. Let's recall what are prime numbers. Our prime numbers are those numbers which have exactly two factors. And who are these two factors? They are the number itself and 1. That means they can be divided by themselves only. Let's take some example. 2, 3, 5, 7, 11. All these numbers can be divided by themselves only. There is no other number which can divide them, so they are prime numbers. I have not written 1 here. Why? Why 1 is not written? 1 is neither prime nor composite. Why it is neither prime nor composite? Because primes are those which have exactly two factors and composite have more than two factors. More than two factors. But what about 1? 1 has only one factor. That is 1. So therefore it is neither prime nor composite. Now this theorem says that every composite number, I'm talking about any composite number. So let's take an example. I'm talking about 120. I'm talking about 120. 120 is a composite number. And this number can be expressed as product of primes. And this factorization is unique. So that means I need to do its factorization. So 120 I can write as, let's factorize it, 2, 30, 2, 15, 3, 5, 5. So this can be written as 2 into 2 into 2 into 3 into 5. These are all prime factors. It is the product of 3 times 2 and 1 3 and 1 5. But some other child may write it as 2 into 3 into 5 into 2 into 2. Will this change in the positions going to change the number? No. I am just changing their positions. I am writing them in different orders. So I can write it them in any order, but it should be only 3 2s, 1 3 and 1 5 only. I can't write it 4 times 2. So the order can be different. Apart from the factorization is unique. Only these numbers will be used. Only these numbers will be used apart from the order in which the prime factors occur. So they can be written in any order. Let's understand how to find LCM and HCF of numbers by prime factorization method. Here we can see HCF is actually equal to product of smallest powers of each common prime factors in the numbers, and LCM is the product of highest powers of each prime factor. Let's understand it with the help of example. Let's take, we want to find the HCF and LCM of the numbers 6 and 20. Now, since it is the method of prime factorization, so I need to do the prime factorization of both the numbers. I can write 6 as 2 to the power 1 into 3 to the power 1. And 20 I can write as 2 square into 5 to the power 1. Now, HCF. HCF says it is the smallest power of each common prime factor. Now, look at what prime factorization of both these numbers. Who are the common factors here? The common factor is only 2. And I need the smallest power of that. That means I need to check that out of these common factors, what is the smallest power? The smallest power is 1. So my HCF is 2. Now, if I want to find the LCM, so LCM is equal to product of highest power of each prime factor here. Each prime factor involved in the numbers. It is not saying the common factors here. It is saying each prime factor involved in the number. So I have to take all the prime factors involved in these two numbers, in 6 also and in 20 also. I have here 2, 3 and 5. But here I have to find the highest power. When I'm talking about least common multiple, I'm taking the highest powers. And when I'm talking about highest common factor, I'm taking the smallest powers. See to it that it is actually the reverse. When you're talking about highest common factors, it is the smallest powers. When you're talking about the least common multiple, you are talking about the highest power. So now I have to take the highest powers of these prime factors. So you can see 2 to the power 1 and 2 to the power square. The highest power is 2. 3 to the power 1 is the only power of 3 here. So 3 to the power 1 is the highest power of 3. 5 is also alone here. So 5 to the power 1 is the highest power of 5 here. So this is answer is 60. So my HCF is 2 and my LCM is 6. We are also going to discuss one rule regarding HCF and LCM. HCF into LCM is equal to the product of numbers. Let's verify it with the help of this example only. My HCF was 2 here and my product LCM was 20. But my numbers were 6 and 20. So this is also 120 and this is also 120. So for any two numbers, this rule is applicable only for two numbers, not for more than that, not for greater, not for 3, 4, etc. So only for two numbers this rule is applicable. HCF into LCM is equal to the product of numbers. Let's understand how to prove root 2 is an irrational number. We all know that irrational numbers are of the form root, where the number inside the root is a non-square number. Let's take some example. Root 2, root 3. Root 4 is not irrational. Why? Because root 2 is equal to 2, which is a rational number. Root 5, root 6, so on. Now we have to prove that root 2 is irrational. Same can be done for root 3, root 5, etc. Let us assume that root 2 is not irrational. Root 2 is a rational number. Let us assume root 2 is rational. Now, if it is a rational number, it should be of the form P by Q, where P and Q are co-prime numbers. P and Q are co-prime numbers, and the denominator is not equal to 0. Q is not equal to 0. Now, who are co-prime numbers? My co-prime numbers are whose HCF is 0. Let's take some example. HCF is 1, sorry. So let's take example 2 and 7, 3 and 11. They are numbers which are divisible only by 1 and not by any other number. Now, squaring both sides. Squaring both sides. In order to remove the root, I am squaring both sides. So this will be 2 is equal to P square by Q square. This can be written as P square is equal to 2Q square. Now, if I have any number, suppose I have a number 15, then it can be written as 3 into 5. These are two factors of this number, and both the factors are dividing this number. 3 also divides 15 and 5 also divides 15. So here, in the same manner, P square is 2 into Q square. So 2 is also going to divide P square, and Q square will also divide P square. But I don't want Q square. I will say that 2 divides P square. Now, we have a theorem that if any prime number, if P is a prime number and P divides any square number, then P divides that number also. Let's understand with an example. Let me take an example. I am taking 3 as P. Suppose 3 divides 81. 81 is actually square of 9. So this implies 3 divides 9 square. So this implies 3 divides 9 also. So the same theorem we are going to apply here, My 2 is a prime number and it is dividing p square. So this implies 2 divides p also. So if it is dividing p, that means it is a factor of this p. So I can write p to be equal to 2 into some number c. P into some number c for some integer c. For some integer c. Now this is my number 1 and this is my number 2. I am putting number 2 in 1. Put 2 in 1. So this will actually become 2c square is equal to 2q square. Open the whole square. 4c square is equal to 2q square. Simplify it and you get 2c square is equal to q square. What does this mean? This means that 2 can divide q square, c square can divide q square, but I am not bothered about c square. I am bothered about 2 here. So 2 divides q square. So again by the same theorem, if 2 is dividing q square, then 2 divides q also. Now what do you observe? That 2 was dividing p also. See here, 2 divides p also and 2 divides q also. So this implies 2 divides p and q both. So I have found a number which is dividing both p and q. This implies p and q are not co-prime. Because what was the definition of co-prime numbers? That they should be divisible only by 1. Their HCF should be only 1. So they are not co-prime. So our assumption was wrong. We were wrong somewhere. Our assumption was wrong. Root 2 is an irrational number. Root 2 is an irrational number. In same manner, we can prove it for root 3, root 5 and any other numbers. Now let's do some questions which are combinations of rationals and irrational. The previous question was solely on irrational number like root 2, root 3, root 5, etc. But here I have a question which is basically a combination of rationals and irrational. The first few steps are same, but then it is different. Firstly, let us assume that 3 plus 2 root 5 is rational. If it is a rational number, then it should be of the form p by q, where p and q are integers and q is not equal to 0. Now, my main motive here will be to keep the irrational number on one side and take all the other things on the other side. So, firstly, 3 is going to move from here. So, 2 root 5 is equal to p by q minus 3. So, this will be p minus 3q upon q. Now 2 is going to go that side. Here it is in multiplication. There it is going to go in division. So it will be p minus 3q upon 2q. Now just look at my both the sides. This side is an irrational number. But what about the right hand side? As p and q are integers. So what do you think this right hand side will be? It will be a rational number. P minus 3q upon 2q is rational. But this p minus 3q upon 2q is actually equal to root 5. So this implies root 5 is rational. According to the statement, this p minus 3q by 2q is equal to root 5. So if this thing is rational, so root 5 is also a rational number. But this is a contradiction. To the fact that root 5 is irrational. So our assumption was wrong. So our assumption was wrong. 3 plus 2 root 5 is an irrational number. Let's recall now the rational numbers and their decimal expansion. We all know that rational numbers are of the form p by q, where p and q are integers and q is not equal to 0. This is one form of rational numbers. The other form is the decimal form, when we can identify them with the help of their decimal expansion. In that also we have two categories. The first one was terminating and the second one was non-terminating repeating. Now we've also learned how to identify a rational number, whether it is terminating or non-terminating repeating. We know that if the denominator, my denominator q, the denominator q is of the form 2 to the power n and 5 to the power m, then it is terminating. But if my denominator is not of this form, then it will be non-terminating repeating. Let's take an example. Suppose I say 3 to the power 8. I can express it as 3 to the power 3 upon 2 to the power q. Here I don't have a factor of 5, but still this will be terminating. Let's see how. I can definitely make my denominator as 10 cube by multiplying the numerator and denominator by 5 cube. So my denominator will be 10 cube and my numerator will be some number. This number will be 375 upon 1000. So which is definitely terminating. So if my denominator is just a factor of 2, then also it is terminating. If it is just 5, let's check 1 upon 125. This I can write as 3 upon 5 cube. Again, I can make my denominator as a power of 10 by multiplying numerator and denominator by 2 cube. So it will be 24 upon 10 cube. So again, it is terminating 0.024. Another example, let's take as 3 by 40. Here, my denominator is of the form 3 upon 2 cube into 5. I can make this denominator as 10 to the power cube. How? I'm going to multiply by 5 square in the denominator and in the numerator also. So it will be 75 upon 10 cube. So 0.075. So it's terminating. So even if my denominator is only 2, factor of only 2, factor of only 5, or both, then my rational number is a terminating number, terminating decimal expansion. Otherwise it is non-terminating repeating. Let's take an example of non-terminating repeating. 2 upon 75. This can be written as 2 upon 5 square into 3. Now, I will show you this with the proper division, that how this is non-terminating repeating. Decimal, 2s are 150, 50, 0, 6, 450, again 50. Now, every time it's going to give me 50, 50. So, this comes out to be 2 by 75 is actually equal to 0.26 bar. So, this is happening because in my denominator, I have another number except 2 and 5. So, whenever I have a number except 2 and 5, my decimal expansion is non-terminating repeating.